GCSE Physics boosters, force on a current. So this video is about what we call the motor effect, force on a current. Now here are two magnetic poles, north and south, and in between them there is a uniform magnetic field. Okay, now what we're going to do is we're going to put a wire in the field and we're going to put a current through the wire and something's going to happen. So there's a current flowing through a wire which is in the field. And when this happens, what we notice is that there is a force acting on the wire upwards. The wire is pushed upwards. So we have a current carrying wire in the field, and the current and the field are at right angles. And what we get is we get a force which is at right angles to both of them. Okay, so the current experiences a force. Now this happens. Why does it experience a force? What it actually is we saw in another video that the current produces its own magnetic field, and then the two fields interact with each other, and it's something called the catapult effect, and it's basically pushed upwards. Okay, it's nothing mysterious, it's just the two magnetic fields interacting with each other. Now, something you need to be able to do is to work out the direction of the force, and you do it using Fleming's left-hand rule. Okay, when a current carrying wire is in a magnetic field at right angles to it, then it experiences a force which is at right angles to both the current and the field. So don't be shy, get your left hand so that your thumb and your first finger and your middle finger are all at right angles to each other. Force, field, current. Okay, and this is Fleming's left-hand rule. And in an exam room, I would expect to see students actually with their left hands doing this. Okay, the way to remember it, look, FBI. Starting at the thumb, F is the force, the field is B. Talk a bit more about that on the next slide. Magnetic fields, B, and then I is the current. So starting at the thumb, FBI. There's Special Agent Mulder. He's in the FBI as well. He knows all about it. So the size of the force depends on the strength of the field, it depends on the current, and it depends on the length of the conductor. So the strength of the field, B, magnetic field strength is B, capital B, and that is measured in Tesla, named after a guy called Nikola Tesla, who was a very, very, very clever bloke, and he invented a ridiculous amount of stuff. If you don't know about him, look him up. Okay, find a YouTube video about him. Very, very clever bloke, Nikola Tesla. And magnetic field strength is measured in Tesla. The current is measured in amps or amperes. The length of the conductor measured in meters. So the size of the force depends on B, I, and L. In fact, F equals Bill. Okay, F equals B times I times L. In SI units, yeah, F equals Bill. Here's a little question you can have a go at, and it's basically a wire of length, doodah, carrying a current of thingy, magnetic field of strength thingy, everything at right angles. What will the force be? And it's just F equals Bill, and there's the answer. So you should be able to do these now. You should be able to work out the direction of the force. It's either up or down, and the size of the force. So pen, paper, calculator, work them out. I'll show you the answers in 3, 2, 1. There you go. Now in this diagram, it's not just a piece of wire. I've made a rectangle with my piece of wire. Okay, I could have lots and lots of turns, but let's just have one turn to begin with. Now looking at this, in this diagram we have a rectangular piece of wire in a magnetic field with a current flowing through it. Now look at the side AB. Will that be pushed up or down? Then look at the side CD. Will that be pushed up or down? And then what will the coil tend to do because of that? Well, what you'll find is that the side AB of the coil should be pushed upwards, and then CD should be pushed downwards. And so you're going to get a turning effect, a moment. Do you remember we did moments in another video? So because of these forces, the coil will tend to rotate. And that's basically an electric motor. That's what's happening in a motor. Okay, we have a coil of wire which is rotating. So obviously the design of the motor is a bit more complicated than that, but that is the basic principle, which is what we need to know. Okay, here's a DC electric motor. Okay, there's all kinds of things I could talk about. There's lots of different designs of electric motors. There's DC motors, there's AC motors, there's induction motors. But basically it's a coil experiencing a turning force in a magnetic field. It's the motor effect. So the motor effect, electrical energy goes to kinetic energy. Interesting little exercise. How many things in your house contain an electric motor? And I would say at least 20. Okay, there's electric motors all over the place. Now, there's motors. Something else which uses the motor effect is a loudspeaker. Something else you need to know as well. A loudspeaker or headphones, which are just basically a couple of little loudspeakers. Yeah, and a loudspeaker. Now, what happens is you have a coil which is in this circular magnet. You put an alternating current in the coil, which is the audio signal, yeah, from an amplifier, and basically the coil moves up and down. Yeah, as the current changes direction, the coil moves up and down. The coil is attached to a cone, and the cone pushes and pulls the air, and it produces sound waves, which are pressure variations in the air. So as the coil vibrates, the cone vibrates, and that produces sound waves. Okay, pressure variations in the air.